All right. So here's what we're going to talk about today. Definition of a power. And then we're going to talk about where I'm on page 124, 124 of your packet. Okay, and then we're going to talk about the properties of exponentiation. Okay. The definition of a power. When you have something like 3 to the 5th or x to the n, that's called a power. A power is made up of a base. So 3 is the base and 5 is the exponent. Okay. And then 3 to the 5th, the entire thing is called the power. 3 to the 5th, the whole thing together is called a power. Sometimes we use the word exponent and power interchangeably, and it's not really correct. The exponent is just the thing up here on top of the base. This thing is the base. The entire thing is the power. So a definition of a power, when you have 3 to the 5th, it means you have 5 3s multiplied together. Okay, or x to the n means you have x used as a factor n times, or it means you have n x's and you multiply them together. Okay, so when you have x to the n, it means you have n x's. So you have 5 3s multiplied together. 3 times 3 times 3 times 3 times 3. Multiplying that out gives you 243. Okay. Now it says memorize the following powers. I'm probably never going to give you a quiz and say, tell me quick, what's 19 squared? Or tell me quick, what's 7 to the 3rd? But if you study these, becoming familiar with everything on this page, that's just going to help you. It's going to help you as we go through all of chapter 6, doing logs and exponents. Okay, so you can fill these out. 3 squared is 9, 4 squared is 16, 5 squared is 25. I'm not going to do it for you, but you should recognize these numbers. When you're looking for perfect squares, you should recognize numbers as perfect squares. For example, 20 squared is 400. When you see the number 400, you recognize 400 as a perfect square. 15 squared is 225. When you see the number 15 squared, you should recognize that as a perfect square. Perfect cubes as well. 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and so on. Fill these out and familiarize yourselves with the perfect squares and the perfect cubes. Now, these are powers of 2. So powers of 2, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, 2 to the 5th, 2 to the 6th, 2 to the 7th, 128, and so on. When you see the number 128, it's going to be helpful to recognize that that's 2 to the 7th. You might be familiar that app on your phone, that game called 1024, I think, or no, 2048, I think it's called. And it's all these numbers, because every time two like numbers get together, they double. Okay, 2 4s get together and make 8. 2 8s get together and make 64, and so on. So you have all the powers of 2. And so on. Then powers of 3 also, 9, 27, 81, and so on. Okay, so I would fill that out and study those. Okay, let's talk about the properties of exponentiation. Okay, so the different properties we've got, and I know you're familiar with these, but it is worth going over these and talking about them. They're fairly easy when taken one at a time, but then when you have a problem where you're incorporating or applying a bunch of different rules, it is really helpful to understand and be able to verbalize and communicate what each of these products means. Okay, so the product property, when you have a product of 2 powers with the same base. So it's very specific. You can't have 2 powers multiplied together if they have different bases. You can, but you can't apply this product property. So algebraically, it's something like x to the n times x to the m. When you're multiplying 2 powers, this is a power, and they have the same base. They have different exponents. But when you're multiplying 2 powers with the same base, you leave the base alone and you add the exponents. Okay? So an example, x to the 3rd times x to the 4th You're multiplying two powers. The bases happen to be the same. We're going to leave the base alone and add the exponents. Okay. And this is where usually people don't make a mistake on this, but sometimes people make a mistake on this. If you have 2 to the 5th times 2 to the 7th, a lot of times people want to multiply those bases. You can't multiply the bases. You have a power with a base of 2, a power with a base of 2. You leave the base alone, and then you add the exponents. When you think about why that works, it really makes sense. X to the third is 3x's, x times x times x. X to the fourth is 4x's, x times x times x times x. And if you multiplied all these together, you have 7x's, so x to the 7th. Same thing. 5 twos and then 7 twos. You have a total of 12 twos multiplied together. Okay. Now, verbally, what in words? How do we say what this property is? Okay. So when multiplying two powers with the same base, and that's important, with the same base. Okay, you're going to leave the base alone. And multiply, I'm sorry, and add the exponents. Okay. Next one, the quotient property. It's very similar, but you're not multiplying. A quotient is when you're dividing two things. A product is when you multiply two things. So if let's say I have x to the m and I'm dividing by x to the n. Okay. So you can divide two powers if they have the same base. You leave the base alone and you subtract the exponents. Okay. So an example, something like x to the 5th over x to the 3rd. So you leave the base alone and you subtract. 5 minus 3 gives you 2. And it really makes sense if you think about that. And if we put that up here, x to the 5th, you have 5x's multiplied together. And then if you divide by x cubed, 3 of them. The reason you're subtracting 3 is because that's how many canceled. And you're only left with 2. So that's why you have x squared. Okay? Or 3 to the 8th divided by 3 squared. Okay, leave the 3 alone. Sometimes people want to divide the 3's and get 1. Well, you basically lost the problem if you divide those. You leave the base alone. Leave it as a 3, and then you subtract these two together. Okay. Now, you might be asking what happens if the exponent in the denominator is bigger. Well, let's see what happens. If I have x to the 3rd over x to the 5th. There's a couple ways to think about this. You can still do that rule, x, and then you've got 3 minus 5, which gives you negative 2. That's correct. Sometimes you don't want a negative exponent, so you might have x to the 3rd over x to the 5th. So in this case, you can leave, you're going to end up, if you wrote this out as x times x times x, and then 5x's on the bottom. And 3 of them will cancel, and you end up with 2 left on the bottom. So you can call it a 1 over x squared. So you really could call this, if you want, you could say that this property also works by saying if you have x to the m divided by x to the n, you could say x to the n minus m on the bottom. Because if this number is bigger, you want the exponent to stay positive, you would take this number and subtract this number, just like x to the 5 minus 3 would be 2, but they'd end up on the bottom. Okay. So verbally, what does this mean? When dividing two powers with the same base, leave the base alone, and subtract the exponents. Okay. Now, a power of a power property. When you have a power of another power. So let's say we have x to the n, and that's a power. You take that entire power raised to another exponent. Now this entire thing is a power, but it's a power of another power. Okay? And in that case, we multiply the exponents. Okay? So you have x to the third raised to the fifth, you get x to the 15th. If you think about why that makes sense, that's really x to the third times 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 x to the third. You have 5 things. Each of those 5 things is an x to the third. And if you took each of these, x times x times x, you have 5 groups of 3 x's. Right? So you'd multiply them together. Or you could say something like 5 to the third squared would equal 5 to the, you multiply the exponents to the 6th. Okay? Verbally, what does that say? When taking the power of another power, you multiply the exponents. Okay. Now the next one, the power of a product. So if you have a product first, x times y, and you raise that to any exponent, put an exponent on it. So now you have a power of a product. Well, that n actually applies to both of these factors in your parentheses, both of these factors in the base. Okay, you could say it distributes. Okay, x to the n, y to the n. Now, the reason you have to be careful there, or you have to think about this a little bit differently. We know that if those two if the two numbers x and y, if they were being added together, if you had x plus y raised to the n, this doesn't apply to both. Okay. For instance, the classic example is x plus y squared. You can't say x squared plus y squared. You'd have to FOIL. So this, you have to say x plus y times x plus y times x plus y dot 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 n times. So if it's x plus y to the 5th, you'd have to multiply them out. You'd be distributing for days. Okay. But in this case, when it's a product raised to an exponent or a power of a product, it does distribute. Okay. So an example would be something like, let's say you've got 2xy squared raised to the third. Okay. So we have to apply that to each of these factors within that product. So 2 to the third times x to the third times y squared to the third. Okay. 2 to the third is 8. X to the third, and then y to the second raised to the third is going to be y to the 6th. Okay. And verbally, when taking the power of a product, okay, you must apply the exponent. Apply or distribute to each factor in the product. Okay. In the next one, these two kind of go together. If you have a power of a quotient, so you have a quotient x divided by y raised to the n, okay, that's going to be x to the n over y to the n. So that exponent applies or distributes to both the top and the bottom, the numerator and the denominator. So another example would be 2x squared over 5, and let's raise the entire thing to the third. So you've got the top, 2x squared to the third, over 5 to the third. So this would be 2 to the third is 8. X squared to the third would be x to the sixth. 5 to the third would be 125. Okay. So in words, when taking the power of a quotient, you must apply, or we could say distribute, the exponent to the numerator and the denominator. Okay. Now I want you to try all these problems down here. I will post the solutions. I'm not going to do a video of going through all of these, but I want you to work through those, and then you can check the video notes, which will have this all filled in. And before we finish, I want to talk about one more thing. So we're not going to talk too much about 6-4, but one thing that comes up quite a bit, if you go to page 127 in your packet, okay, and this is actually going to be part of the 6-4 video notes, but these two things come up and will come up before we get to 6-4. X to the 0. Any base raised to the 0 is always 1. Okay, as long as your base is not also 0, because that would give you kind of a conflicting message. Usually 0 to the anything should be 0, correct? 0 times 0 times 0 times 0 times 0, no matter how many zeros, it's still 0. But then we say anything to the 0 is 1. So if you have 0 to the 0, you kind of have conflicting messages. Okay, so this is actually undefined when both of them are 0, both the base and the exponent. And you talk about that a lot more in calculus. Okay, but for our purposes, anything to the 0 is 1. X to the negative n, we kind of saw this with the quotient rule, but x to the negative n is equal to 1 over x to the positive n. Again, assuming that your base is not 0. Okay, so something like if I have 3 to the negative 5, well, when my exponent of my power, remember the whole thing's a power, is negative, when the exponent's negative, and I want to make that exponent positive, well, I have to move the entire power down to the bottom. And I still have the entire power, but now the only difference is the exponent is positive. Okay? You can do the same thing if it's in the bottom. If I have 1 over, let's say, 5 to the negative 2. If I want to move this power up to the top, or if my goal is to make the exponent positive, well, now I move the power to the top, and the exponent changes sign. Okay, so this really is just equal to 25. So these are two rules that you'll see, and I know that you know these rules from Algebra 1. Okay, and that's all for now.